Set 49 is really big, so we're going to do this in two parts. 49, part 1 today, and 2 tomorrow, or Friday, Monday, whatever. Okay, so it's all about second derivative today. The second derivative tells you a ton, besides the obvious physics applications, what the second derivative of motion is, acceleration. There's a lot of other things the second derivative does for us, just graphically, and what a function changes. In fact, just this morning, I was riding my bike up this hill, and I was thinking second derivative. Because as I was riding up this hill, it was getting steeper and steeper and steeper, and when I got to this point, I felt good. Why? Because not so much halfway, because at that point the slope starts to even out and get a little less and less each time. And that's called an inflection point. And that actually comes from the second derivative, among other things. But let's talk about the second derivative. So here we go. First derivative tells the slope of a graph, right?
Yes.
We know that, yes? Now the second derivative, by nature, is the change in the first derivative. So if the first derivative is slope, and the second derivative is change of the first derivative, then the second derivative is change in the slope. There you go. So putting these two together, the second derivative is change in the slope. Now, if the second derivative is positive, then that means the slopes are increasing. The second derivative is positive, the slopes are increasing. Yes, I guess you could think of a smiley face. Positive second derivative, yeah? If you look at these slopes, this slope is maybe -3, now the slope is -2, now the slope is -1. Now students might think, oh, those are decreasing. Well, remember, we're talking negatives. And don't you increase when you go from -3 to -2? Yeah, so don't look so much at the numbers, but in terms of the number line, -2 is greater than -3. 0, 1, 2, 3. Now, it's concave up. Oops, we call this, sorry, I didn't actually get to my point. We call this concave up. Okay? Concave up is when, if you draw a secant, the secant is above the curve. Anytime, for example, if I were, that's a humdinger. If I were to connect points on any concave up curve, that secant line will lie above the curve, yeah? Okay. If the second derivative is negative, that means the slopes are not negative, but decreasing. Okay? The change in the slope is negative, so the slopes are decreasing. If you look at a decreasing slope, that's a negative. That's negative. Say wah wah. Okay, wah wah. So we call this concave down. Yeah, it doesn't. If for any reason you do calculus in Europe or something like this, they call this concave convex. But we don't, in America we call it concave up and concave down. Okay. They would call this convex, but we call this concave down, and it is anytime the secant is below the, bless you, wow, the curve. Okay. Now, inflection point then is about concavity, but what do you see going on about concavity? Before that point it's concave up, but after that point it's concave down. Inflection points are changing concavity. We'll get to that in a minute. I'm getting ahead of myself. First, let's get some basics here, right? So this has to do with improved now curve sketches. The first derivative tells us increasing, decreasing, and that's great. But we can get a better graph with the second derivative. Second derivative tells us concave up or concave down. So in part A, I give you some information. I say for all x's, the graph has a positive first derivative. Now, if the derivative is positive, what does that imply about the graph? Of f. It's increasing. Remember, the derivative tells us if it's increasing or decreasing. The second derivative tells us if it's concave up or down. It says the second derivative is positive, so it's concave up, right? So based on that, I want you to sketch what the graph could look like. What would it look like to be increasing and concave up? So here's concave up, but can I use that whole curve? No, I want it to be increasing only. So you would take the piece that is increasing only. Give me an example of a function that's exponential. Yes, exponential. Yes, well done. Okay. Do you get the point? Try B on your own. Actually, let's do B together, and then the rest on your own. So, what do these two things tell you about the graph? Decreasing, concave up. Here's the concave up graph. I want the decreasing part, so I want to sketch only this guy. Yeah? All right. Try C. Show your graph in the air. Like this? Just this? This? No. This side? No. This side? Yes! All right. Wow, good energy. Okay. Yeah! Yeah, man! Decreasing concave down. I love it. Okay. So the next row is two regions. So we'll do one together, then you'll try something else. So from negative infinity to 0, or the left side of the graph, tell me what two things are happening in. Andy, speak up. They're all talking for you. Decreasing concave up. Wonderful. Okay? So if it's decreasing concave up, I first imagine the whole concave up, but the decreasing only part is this part, right? Put 0 to show, okay, now we're going to change into a different situation. And for the right side, Abby, what's going on in the right side?
It's increasing and concave up.
Increasing concave up. So increasing concave up would be like this. So it seems like we just found a min, probably, yeah? Okay. You understand what you're doing? Okay, try EF, please. Anybody besides Peyton missed the test? Oh, we talked already, so you're going to take it. Yes. Test looking really good, by the way, so far. Yep. Let's assume they are continuous. Okay, that's actually a good question. The lack of continuity makes things much harder. Now, that doesn't mean they're differentiable. There could be sharp turns, things like that. But yes, assume continuity. Ready with those two? Okay, so Corey, what does the first section look like in this E?
It's decreasing and it's concave up.
Decreasing concave up, so it seems like something like this to 0, yeah? And Tim, what about the second section?
It's concave down, but it's increasing, so it's up like that.
So like that? So you get a sharp turn kind of thing there? Okay, cool. F, Mr. Dews, what's going on in the first section of F? And? decreasing concave down. So that seems something like this, yeah? And let's see, Martin, what about the second section? Increasing concave up, so does that look something like this? You got kind of a funky V. Cool. All right. Now you're doing great. Go to G, which is 3 regions. Assume all these graphs are continuous. I should have put that in my notes. Sorry about that.
I like
Okay. One more minute, please. Okay, first region stuff.
It's
Decreasing concave up, so something like this. Okay. What about second region? Let's see. Increasing concave up. What about third region? Who haven't I? Hayden, third region of this G. Increasing concave down, so something like that. You have a kind of a little dipper, big dipper kind of graph? A curvy? Or duck? Or duck? Whatever, okay. Okay, and so last but not least, going backwards, I give you the graph. So up to 0, give me the sign of the first derivative and second derivative, Taya.
plus and then minus.
Positive first derivative, negative second derivative because it's increasing concave down, I agree. From 0 to 2, I'm running out of people. Abby, haha, quiet person trying to hide. 0 to 2, what's going on 0 to 2? Both negative, they're decreasing and concave down, I agree. Who, Jim? Himmy.
It's decreasing.
I see that, yes, so what are the signs? Negative, positive, I agree. Do we all see where we're coming from?
Yes.
Okay, cool. All right, let's go on then. Numerically then, look at a table. These tend to be difficult multiple choice problems, so we'll practice these a lot, and you'll, after practice, feel like, yeah, I'm good. So a derivative is a rate of change, obviously. So the second derivative is the change in the change. That's getting a little wordy and a little kooky, but it is what it is, all right? So when you go to look at a table, if the first derivative is positive, then the function values should be increasing. And if the second derivative is positive, the changes between values should be increasing. So if, for example, I say in this problem, f and f prime and f double are positive for all reals, and I said I give you a little bit of a table, but f of 5 is missing, what would you know about f of 5? Greater than what? F of 5 is greater than 7 because f prime is positive, so f needs to increase. Right? All right, cool. Now that's the easier part of it. Now the harder part is the second derivative. The second derivative is about how the changes are going. Now in this interval, the change was 4, all right? So if the first change is 4 in y in 1 and x, you do really need to look at the x values too. It's changing 4 units of y in 1 unit change in x. The next change should be more. Why? Because the change in the change is positive, because the second derivative is positive. the changes are increasing, right? So, if the next change is more than 4, then f at 5 should also be greater than. So if the next change needs to be more than 4, then this should be more than 11. Okay? So in terms of a multiple choice, they might have, some numbers, some BS numbers, and then they'd probably have 8, which would be tempting because the increase would make that true. But then they'd have 12 or something like that, and that would be a choice. All right. Try this then by yourself. If for the same table, f double is negative. So assume f prime is still positive, but now I'm telling you f double is negative. What do you know about f of 5? Now I'm looking for 2 facts about f of 5.
Greater than 7 or less than
Hey, you say it'll be less than 11, but
Greater than 7.
greater than 7. So now you should say f of 5 still has to be greater than 7. Why?
It's increased.
Yeah, it's because f is still increasing. I didn't change the first derivative thing. The first derivative is still positive. So f still needs to increase. So that means it's got to be more than where we left off, which was at 7. All right? But why do you say it has to be less than 11? Yeah, if f double is negative, then the changes need to be smaller or decreasing. So the next change is less than the previous change of 4. So if it was at 7 and it needs to change less than 4, then that means it would have to end at something less than 11. You follow? Okay, we'll practice those. Okay, let's go analytically. This is the most common question, at least in our book. So, given an actual curve or an equation, is the curve concave up or concave down at x equal to? Justify your answer. So, would you write this really quick? F is concave up if f double is positive. F is concave down if f double is negative. I'm okay if you abbreviate CU and CD in my homework. On the AP test, you will write concave up and concave down. Okay? So, is all right, so what do we need? We need to take the derivative. I can't get to that. There's kind of an IVT idea to the derivatives. You can't get to the second derivative unless you pass through the first derivative. 3x squared plus 4x minus 4. What is f double? 6x, 6x plus 4. Yeah? All right? So now what do? Do I need to find the zeros, do a sign test, or should I just plug 2 in? Just plug 2 in. I could do a sign test and get the regions where it's always concave, but they are just asking about 2. So let's just put 2 in. And we get what? 16. Justifying our answer then, we would say f is concave up at x equal 2 because f double prime is positive. And you can again write greater than 0 or is positive or worse. Either one's fine. Are we good? Okay. Would you try the next example on your own? Or with your amigos? ¿Listos? ¿O not yet? Not yet. I sure wish I would have kept those derivatives up on the board, huh? No. Good job. Okay, catching up. Jake, what's the first derivative of tangent?
Secant squared x.
Secant squared. Good job, Jake. You have so many voices. F double, then. It might help to think of secant squared. I know we write it kind of funny, but really it's that. So it's now a function within a function. Therefore, we must take the chain rule. So, Evie, what's the derivative of secant all squared?
2 secant squared of x.
Okay, I agree. I'm going to get there in 2 steps. The derivative of the outside is 2 times secant squared to secant to the first, yeah? But then the derivative of the inside is secant of x tangent of x. That's where she was getting secant squared. We picked up another secant eventually. And you can leave it expanded or combine it. I don't care which one. But we still need to do what? Evaluate a pi over 4. So, how are your trig skills? What is the secant of pi over 4? So tangent is cosine is root 2 over 2, so what's secant?
2 root 2 over 2.
2 root 2 over 2, or just root 2. However you choose to do it, you need to then square that, and we'll get to that in a second. What is the tangent of pi over 4? 1. So I'm getting 2 times 4 over 2, and 4 is your answer. Okay? All right, would you please scratch this? This is, I don't know what I was thinking. A place where the graph changes concavity. That is not true that it can't be an extreme. Actually, that's one book that says this, but the majority of these college texts do not. So scratch that out, please. It's called an inflection point. Inflection points could be something like this. This is an inflection point because it's changing concave up to concave down. This is an inflection point. If you have something like this, that's an inflection point because it's changing. Nope, that's stupid. That's not changing concavity, is it? I'm dumb. My bad. Okay. What was I thinking? I don't know what I was thinking. I was thinking, sorry. So, would you actually add one more thing? A place in the domain of F. That's necessary because if you think of this graph here, I think you'll agree that that graph changes. Yeah, okay. Changes concavity at 0, yeah? But is there an inflection point at 0? No, there's not a point at all at 0. So that's ridiculous. So this is not an inflection point at 0 because it does have to be in the domain. Okay, that going on then, a cube, so actually, would you get these steps, and I kind of wanted to put these in your notes, but finding an inflection point, you first need to find where the second derivative is 0 or dne. Because if it's going to change concavity, it must be the case that the second derivative is going to change sign. So we first find the zeros, that's where it's going to possibly change sign. So let's get the first derivative. 3x squared plus 4x minus 4, and then blow right past that into the second derivative. Second derivative is this the same question as before? Yeah. Oh, sorry, 6x plus 4, yay? Okay, now this could change sign. The second derivative could change sign where the second derivative is 0. So now find the zeros, and that happens at negative 2/3. Now, sign test the second derivative to see if there's a sign change. So, for example, if I sign test the second derivative before negative 2/3, like at negative 5,000, the second derivative is negative. And after, at 5 billion, the second derivative is positive, which means the graph, in a cubey kind of way, went concave down to concave up. That makes sense. So we would conclude then there is an inflection point there. The bummer is that the whole thing is you're finding an inflection point, not an inflection X. So what else do I need to do? Yeah, okay. If it is an inflection point, if there is a sign change, you need to find the y that goes with it. Now, then it's always dangerous because you got three different equations to work with. When am I going to plug negative 2/3 in? The second derivative, the first derivative, or F? F, yeah. You're looking for points on the original graph. So F at negative 2/3, I wish I wouldn't have made this problem, but oh well. Negative 2/3 cubed, I can do that, don't be a wuss. Negative 2/3 squared, no problem. We're educated people, right? All right. Don't want it there anyway. All right, negative 8/27. What do we got there? So 4/9 times 2, so 8/9, yay. Plus 8/3 minus 1. Do you concur? Hey, common denominator is 27, so negative 8 plus what? 24 plus what? 72 minus what? 27 is, this is the student's least favorite part by far. So what do we have there? So we got your 16, 88, 50, 61? Do you agree, or are you just going to take my word for it? Yep. You're the teacher. As if I learned advanced fraction reducing in college. I think we got the same education in terms of adding fractions, you know? We both know how to do it, I think. Or not. Okay, so the inflection point is, all right, would you also throw in there, if it requires justification, required, then it is F, not F prime, F double, it's easy to get confused of the subject of this sentence. F has an inflection point at, again, I will abbreviate inflection point, but on the AP test we won't, negative 2/3, 61/27. Because, now would you write this please in your notes? Because F double equals 0 there, would you write that, but put a big old X through it? Because that is not the test for inflection point. It's because F double changes sign there. Okay? And that is a very common mistake. People say F double 0. Look at F equals X to the F equals X to the 4th. Okay, where's the graph of F equals X to the 4th? It's like a really steep parabola, yeah? And if you look at the second derivative, isn't the second derivative 6x squared? Yeah? Does the second derivative equal 0 to it?
No, wouldn't it be 4?
No, it's 4x to the third, not 3x.
All right, now my point is lost. Stupid bad derivative skills. Well, x squared, how's that? Okay, would you agree that the second derivative is 0 at 0? And yet I think you'll agree there is not an inflection point at 0 because it does not change concavity there. And so it is crucial that you investigate, does it change sign? Not just is it 0, call it good, get lazy. You've got to verify it changes sign. Understood? Okay. What the heck is this? All right. Is this the last thing? Okay. Now, this is a summary of the big ideas where the derivative, second derivative is positive, is concave up. F is concave up. So on. This is what I want to get on there. Would you sketch this cube 3 times, please? This cube is, you could say it's x times x minus 1 times x plus 1. There's odd symmetry there. I want it to look just like that. Actually, it's x minus 2, x plus 2. And the peaks are at 1 and negative 1. Sorry about that. These should have peaks at -2, or sorry, x-intercepts at -2 and 2, and peaks at -1 and 1. You down? Okay. Now, if this is f, the first one I'm going to say, that's the graph of f. And there's an inflection point. F has an inflection point at what x? X equals 0. Okay? Because at that point on the graph, we're changing concavity, okay? Okay, now that one's straightforward. Now, in the second picture, now I'm saying that's the graph of f prime. Where does f have an inflection point? -1 and 1. Why? Okay, because f prime slope changes sign. And what is f prime slope? Isn't that f prime's derivative? And f prime's derivative is f double prime. Okay? F double changes sign. Okay? Last but not least, now I'm saying that's the graph of f double. Where does f have an inflection point? And 2, because f double changes sign. Okay, you follow? Okay. I don't know why I failed to get some of those on there. All right, that's good. Let's move on to not this. Questions on 40. Do you start 47? 47. 0 or less questions. Go. Okay, 1. If we get to 48, great, but we are going to guarantee at least get to 47. Okay, 47, 1. Anything else? 26? Okay. Okay, let me know if you have anything else. All right, so in 1 it said a 13-meter long ladder leans against the wall. The base is pulled away from the 2 meters per second as the top of the ladder came. So did you draw a picture?
Yeah.
Okay, you need to establish what is always a number and therefore put that number in, and what might change. Does the ladder's length of 13 change, or is it always 13?
Always 13.
Always 13. Feel comfortable in putting it in. Okay? Later it says, how fast is the top of the ladder moving when the base of the ladder is 5 meters from the wall? Does that mean I put a 5 here? No. Is it always 5? No. Don't ever put the instant in your picture. That's a moment in time, but it's not always 5. Call this, what did you call this, X?
Yeah.
X and Y. All right. In terms of what's given, it says the base is pulled away at a rate of 2 meters per second. When you see that word rate, that's the calculus given. If the rate is 2 meters per second, then that means the derivative of something with respect to time is 2 meters per second. What is the derivative of what? It's x, dx dt, because if the base is being pulled away, then x is changing. If it's being pulled away, is x increasing or decreasing? It's increasing. So we got a positive. That's important that you interpret the sign 2 meters per second. All right? Now, the question is next. That's given. What do they want and when? What did you say to that question? Yeah, they say this is obviously sliding down, so how fast does this slide down as this pulls out? So dy dt at the instant When x is 5, did you say? Okay. Okay. Some teachers might say make a second picture for the given. We'll get to that in a second. But what's an equation? I can't find any derivative until I have an equation to take a derivative on. So what's an equation that relates to variables? Okay, Pythagorean theorem. X squared plus y squared is 13 squared. Okay, I have an equation, but I want derivatives. So now what should I do? Take derivatives with respect to x, y, or t. T. So when I take the derivative of x squared with respect to t, it's the derivative of the outside, which is 2x, but times the derivative of the inside, which is dx dt. Then the derivative of y squared. The chain rule derivative of the outside is 2y, times the derivative of the inside, y dt equals the derivative of 13 squared is just 13 squared, right? Oh, it's 0, because it's a derivative of 13 squared. Okay, cool. Did you leave the 2's or dump the 2's? Dump the 2's. If you divide the whole thing by 2, then those are divided out. Cool. Now, this is what we're looking for, dy dt. And that means we have to plug in for all the other three things, yeah? What's x? 5. And what's dx dt? 2. The hardest part is they don't give you the y explicitly. So how do we find the y? Yeah, you look at the case of, oops, I drew my triangle wrong, but when x is 5, the ladder's 13, that implies that y has to be 12. That's a primitive, or a Pythagorean triple. And so if y is 12, then that leaves you with dy dt. It looks like dy dt is going to come out negative. Tell me why that's logical. Now, y is decreasing. It's sliding down the wall. Y will get smaller, and therefore its rate of change is a negative one. What are the units? Meters per second. Okay, 26. I assume that's a replacement, so let me get that real quick. Strangers in the night, exchanging glances, wandering in the night. Ooh, that's a humdinger. Where's 26? What? Oh, that's 48, my bad. Sorry. Okay, 26, is that this guy then? Yes, all right. Okay, classic. All right, so here we go. I guess this, you could say this is a known picture, but I'm going to draw it anyway. So we got a cone of sand with a radius and a height, yeah? All right. Sand is pouring in at a rate of, there's that key word, rate. Look at the units. Tell me what's given in calculus. dV dt is positive or negative? Positive 2 cubic feet per second, yeah? Okay, what do they want and when? You could look at this height as half the diameter, and you could say that's a given. We could use it now and put it as a given. We could use it later. What do you want to do?
I put it in now.
Okay, so if the height is half the diameter, then I'll figure out what to do with that later. The question is find the rate at which the height is changing. So they want the h dt, and when do they want it besides now? When v is 200, yeah? All right, so this one is hard because the equation for volume has 3 variables. And if I can avoid doing calculus on 3 variables, I want to. So how do I avoid it?
Half the diameter.
Yeah, use this idea. If height is half the diameter, doesn't that mean height is the radius? So should I put in for HR and make it all R, or should I put in for RH and make it all H? Why all H? Now you want the H to T, so you want H to stay. Okay, so You're gonna plug in for R and get pi over 3h cubed. We? Okay, now let's take the derivative with respect to time. What is the derivative with respect to time? dv dt is pi h squared dh dt. This is what I want. So I need to substitute in for everything else. What's dv dt? 2. And what's the height? Don't know that. So how do I find what the height is? Solve the volume. Which of the volume equations is the best place to go? This one or this one? The second one, yeah? So 200 equals pi over 3h cubed implies h is 600 divided by pi, then cube rooted, yay?
Yeah.
Okay. So this would be something like 600 over pi cube rooted and squared, or to the 2/3 power, or something like that. Okay? Okay, so dh dt then is 2 over that, yeah, that monstrosity. 2 over pi times 600 over pi to the 2/3. What are the units? Feet per second, right? Yeah. Okay. Yeah, we're good. Okay. Any other questions on 47? Cool. 48. Questions on 48? 12. 22. Okay. 48, 12, and 22. Is 12 normal book?
Oh, right, yeah, this one.
All right, 48, 12. Suppose f is x squared plus bx plus c, or b and c are real numbers. Use the first derivative to determine where the min occurs. First derivative to determine min. Okay? So really, I don't know if you get this or not, but they're really trying to get you some kind of quick way for finding the vertex of a parabola. Isn't that where a min happens? All right. So let's go with the derivative. Isn't it 2x plus b?
Yeah.
And isn't that 0, or you have a critical number at, do I solve that for b or x? X. X is negative b over 2, yay? Okay, so I don't know if they want me to do a sign test. I guess they say use a sketch. Now, it seems like that's a min because that's how a parabola opens that's positive, yeah? So we can find the x of any vertex by just taking half the b. So if I said, hey, here's a parabola, x squared plus 17x plus 5. Where's the x of the vertex? What's b? 17, so it's negative 17 over 2. Okay. Now the y you have to plug it. That's kind of cool. Okay. 22. Question on 22. All right. Did I changed it on the paper?
No, you just said you made a suggestion.
A suggestion? Oh, yes.
You want us to do it with calculus calculator?
Yes. That'll be way more fun that way. Wouldn't you agree? Calculus, not calculator. Calculator is for the week. This isn't calculator class. This is calculus class. This isn't AP calculator. Right? So, quotient rule or break it up first?
Quotient rule.
Break it up, break it up. Okay, so what is the derivative? 1 plus 0, what's the derivative of x to the negative 1? Negative x to the negative 2, yeah? So this is 1 minus 1 over x squared equals 0 or undefined. Should I clear the fractions or get a common denominator? Don't clear the fractions, you lose critical numbers that way. Instead, get a common denominator. That's a trick question. Sorry, I misled you. Okay, so if you get a common denominator, I think you, oh, shucks. So what are your critical numbers? Just 1 and negative 1. But they said x is negative, so just 1, negative 1. So go. So, can you put these both in?
47.
We got through all the questions. Did we? No, there's no more. No, you didn't say it.
There's always more.
All right, 47 only. All right. There you go. What? You just at the end of the day, you just.
It's my handwriting.
Oh, well, there you go. That explains a lot. Wow. I hope the learning's there. Autopilot.